realized I left some reading summaries upstairs. So after 31, I think I'll collect these, but then run up and grab them and bring them.
Oh, that's fine. Yeah. Go ahead.
Classes
Okay. How many students are still in the class right now?
So officially, so I think upper 60, 65.
Are still that any? Good.
Maybe. So we just found out that a few dropped this week, so it might be down to.
Yeah. I think there might be a milestone for dropping, right?
For at the low end or at the high end?
I don't know. I think that like a dropping class probably cannot happen over the entire semester.
Oh yeah. The cutoff was like this week. Yeah, you're right.
Right. Okay. Yeah.
Yeah, we should probably check that. I know a few. We heard from like a couple project groups lost a number.
Right. Okay, I will get started. So on Monday, we basically we covered two fancy MCMC algorithms, and we had a few more to cover. And I mentioned to you earlier that we can actually go endless and cover many more, fancy techniques for approximate inference, MCMC or variational inferences. I think I decided to probably stop at this point, giving you more ideas for MCMC, because these are very technical small topics which actually could be digested by offline reading, or we can find more time later to address some of this if you find them interesting. I want to actually now bring you guys maybe back to the basics of graphic model and discover a few new techniques of designing fancier graphical models. Okay, the inference technique is useful, but I think we've gone through almost 6 or 7 lectures on that. I think probably some of you guys feel bored about that already. So today we're going to actually study some very interesting recent techniques in enhancing the power of graphic models. And in the next 3 lectures, we're going to examine this topic known as Bayesian nonparametrics. How many of you guys heard about these keywords, Bayesian nonparametrics or nonparametric Bayesian inferences? You probably heard about that, right? And it's a rediscovery made by some machine learning people, some statisticians in the past decade, from reading good old day papers in the 60s and 70s. So it is about addressing this problem. In fact, many of you guys asked me these problems, in 701 or in some other classes. So here is a classroom problem, and we have a number of ways of solving that. You can run k-means for that. You can also do what? Any graphical model good for this problem? A mixture of Gaussian models, right? And I think many of you guys probably want to ask, how can we set that magic K? What is the right number of that mixture components? And at that time, I usually hand wave and say, okay, try a few different Ks, or there is really no good answer for that. At least there is no principal answer for that, right? So the technique I'm going to talk about today is going to give you at least one way of addressing this problem elegantly. Okay, at least there is a theory behind that to allow you to do Bayesian inference over the number of Ks, and you treat basically the number of clusters to be by itself a random variable. And you can have similar problems in different domains, right? So here is a typical image segmentation problem, and you can also ask how many segments there are in this image. You can choose to pick the main ones, but how about all these people and other things, right? And always there is a tricky balance about how fine-grained you want to go in getting the segments or in getting the clusters out of this kind of problem, right? To the extreme that you can make each point a cluster. And at that point, you actually are reaching another domain in statistics called non-parametric statistic, where if you remember this Poisson density estimator, we're going to put a kernel function on each of these points and add them together. And that actually also give you a density estimation, right? And what we're going to do today is to go somewhere in the middle, because maybe someone can suggest to me what is the pitfall of using a pure non-parametric approach where you put a kernel on every point, like this. Like I put a kernel here, kernel here, and then my P of x becomes what? Becomes the sum of n over 1, a kernel f of xi. What is the problem with that? The alternative thing is a P of x equal to a sum of pi I and f of mu I and sigma I, right? So here sum equals to 1 to maybe 3, and here it is 1 to n. So what is the pitfall for this approach, purely non-parametric? Yeah, this is definitely not a big data solution, because what if I have 1 billion data points? I'm going to store all of that, right? Not a good idea. What is the pitfall with this approach? You don't know the number of k. Why it's 3? Why it's 4? And also, you need to make strong parametric assumptions on every clusters, right? So what we're going to do today is to ask what is somewhere in the middle. Okay, can we be somehow Bayesian non-parametric? And here is another example, when people are nowadays doing topic models all over the place. And again, you can always ask, given you maybe not just a corpus, give you a time series of corpus, and how can you determine the number of topics, but also to determine the lifespan of topics, right? When a topic starts and when they end, and so on and so forth. So these are really the kind of problems very good for a non-parametric Bayesian approach. So here is a opening slide about a comparison between the two extremes. So far we've been studying parametric models, right? Here we assume that all the data can be represented by a fixed dimensional model. Okay, it doesn't have to be only cluster model. HMM or any graphic model, you first by assuming what is the dimension of the data, how many hidden states you have to include in HMM, and so on and so forth, and then you're going to learn the parameters, right? And this is basically once you have that model learned, you can throw away the data, and then only rely on the fixed dimensional model you learned. And then I just briefly mentioned this non-parametric approach. The number of parameters, the complexity of the model can grow with the data. Right? So this Bayesian non-parametrics is an interesting approach. It is allowing, in principle, infinite number of parameters a priori. Okay, sometimes people call these models infinite models, which is a little bit misleading, because you are having finite data set, no matter how big the data set is, how come you need an infinite model, right? It's not necessary. But what really it means is that it has infinite capacity to accommodate any data. If you have more and more data coming in, you don't have to redo the model. You use the same model which can grow itself to accommodate new data. And the way it does that is to define a prior distribution over the model space, which is infinite dimensional. Okay, so it doesn't matter how many cluster centroids, how many hidden states you have to use. There is always a non-zero probability of growing that far. And the finite data set, of course, when it is to be used for learning the model, it will, of course, only define a finite dimensional model using a finite number of parameters. But again, still, in the finite space, how many is the other question? And you can use this Bayesian inference to approach a posterior, posterior estimation of what might be the best number for modeling data. And the other parameters, they disappear. But technically, in theory, you can say they got integrated out because their value no longer matters. So this is the whole big picture. Let's start developing that model by actually growing our finite dimensional finite mixture model, okay, and see how actually we move into that direction. So here is a clustering problem. And as we said, one of the good model for that is to apply a mixture of Gaussian model, which I wrote here. You begin by assuming k clusters, and then you are going to introduce placeholders for a finite number of parameters. In this case, the mu and the sigma of every k cluster, and their prior weights. And then you are going to plug in the data. I think here it shouldn't be infinite. It should be n, and then let's define the likelihood of data, right? So we are all familiar with that. And then, if you want to be a Bayesian for learning this model, so that means you need to treat the model parameters to be random variable itself. And they all follow a prior distribution. So what are the random variables, or what are the parameters to be treated in this way? So in this case, we have the pi, we have the mu, we have the sigma, right? And what we need is to now define prior distributions for each of them, right? And then if you want to still write the likelihood of data under a Bayesian model, now you need to integrate out all the model parameters. Okay, of course, in each of these prior distribution, there are hyperparameters, and these are unknown constants, which we discussed before how to deal with that. Okay, and of course, there are good practice in picking the easy to work with models here, right? You want to make them Fourier conjugate, so that you can make the posterior inference easier. Right? So let's see. A conjugate prior for the mu could be what? Could be a Gaussian Weichart prior. Right? And later you will learn that this will follow maybe a gamma prior. And the pi, which is the mixture weights, what is a good prior for that? It is a Dirichlet. So let's take a look at the Dirichlet. Dirichlet is actually a very interesting distribution, and today I'm going to spend some time to really tell you some interesting properties of this distribution, and then use it as a vehicle to drive to an infinite dimensional model. So here is a Dirichlet distribution, okay, and this is the argument, right, and a vector of pi is following a Dirichlet if its density can be written in this way, okay? And the gamma, the alphas has to be bigger than 1, and greater or equal to 0, and then at least one of them has to be absolutely greater than 0, okay? And these are gamma functions, which are normalization constant for this distribution, okay? So we all know that already. And if a pi follows a Dirichlet of a k dimension, then pi is by itself a multinomial vector, right? It means that each pi k is a non-negative number, and they sum to 1 altogether. And here, and also another important property of a Dirichlet distribution is that the random variable, the expectation of the random variable, equals to this, equals to the hyperparameter normalized by the sum of the paraparameter. Okay, so very intuitive. And here are how this density function may look like. So in fact, the take-home message is the following: if these alphas, the hyperparameters, the Dirichlet parameters are very, very small, like very tiny one, then their center of mass, okay, tend to aggregate at the middle of that space. So this rectangle is called a simplex. Simplex means that every point in here, oh, it is red, so I actually use a different color. I use a blue here. So every point in here, if you draw a projection to the other face of the triangle, then all this actually correspond to pi 1. And actually, if this is alpha 1, and if this is alpha 2, if this is alpha 3, then this guy correspond to pi 1, and this guy correspond to pi 3, pi 1, and pi 2. Okay, basically, if it is projecting to a line, then it is on the other side of the surface is corresponding to the corner indexed by that hyperparameter. So these three should add to 1, and such a space is called a simplex. Okay, and here you can see the density is bigger in the middle of the simplex and weaker on the corner. But if the alpha is a bigger value, then the mass actually goes to the corner more. Okay, that's basically some property you want to remember. And if the alphas, the Dirichlet parameters, are asymmetric, then you have a way to skew the concentration. Okay.
What is pi? Is it the distance from the center to the edge?
Yeah, the center to the edge.
So how about
It's just a coordinate. This basically corresponds to that particular vector. It's a random draw from this space. Alpha 1, 2, 3 is the hyperparameter, is the Dirichlet parameter. What's that?
Alpha 1 is the number, it's corresponding.
Oh, no, yeah, you shouldn't take it. Yeah, this, I should just label them 1, 2, 3. Forget about alpha. Okay. Okay. What's that? Yeah, I'm drawing this in this case a three-dimensional Dirichlet. Yeah. We're not yet there yet. Don't ask about non-parametric model. It's a different. This is just a in non-parametric space. You don't visualize it anymore. Okay. And here I'm trying to build you a more intuitive geometric picture, and which when you take the limit of infinity, you're going to that place. I suppose this is trivial, right? This is something we should learn, many, many years ago in our 701. So here I'm just for review. If you are not comfortable with this, go and read those, the basic materials. I meant to say the following more interesting information if you actually don't know about that. So now, first thing about Dirichlet is that it has this very nice property of conjugacy, right? Once pi is from a Dirichlet and the pi is used to define a multinomial for the actual data, then the posterior distribution of pi given the data and also the prior is going to be now a shifted Dirichlet distribution, okay, with actually both the Dirichlet parameter and also their counts, okay, in the real data. That's something you want to remember. Okay, the derivations are pretty much in here. This is the probability defined by the multinomial, and this is the Dirichlet density. And when they multiply together, you see another Dirichlet, renormalized Dirichlet. Okay, and it can be written in this way. It's just a renormalized Dirichlet with the Dirichlet parameter and the counts. That's one thing you want to remember. It is it's a conjugate prior to multinomial. Okay, so we're going to actually now study a great deal about the Dirichlet distribution to make it a vehicle to define distribution over distributions. In fact, the Dirichlet distribution itself is a distribution over distributions, right? Because multinomial is a distribution, it is a distribution over categorical numbers, right? And now we are talking about the coefficients or the parameters for that multiple distribution itself to follow a distribution defined by Dirichlet. Therefore, this is a distribution over distributions. But it is a distribution over a finite dimensional distribution. Okay, so then we can make it even fancier. Right now, the Dirichlet is just defining a prior for the pi. It is not quite a full distribution that we would use to model data yet. It is just for modeling the probability of categorical indices, 1, 2, 3, 4. But for every of these categories, say 1 or 3 or 2, we are going to also able to produce other things, such as we can associate each entry with a mean and covariance. And that basically means that you can define a prior distribution over a mixture of Gaussians, right? The weights is Dirichlet, and the Gaussian mean and the covariance can be drawn from their own conjugated prior, right? Then by that you can define now a distribution over fancier distributions. Okay, so this is the first thing, and let's see how we can now define a Bayesian finite mixture model. Okay, so here we have a Gaussian. Okay, and for Gaussian distribution, we can also draw samples. Suppose that this is Gaussian from which we can draw the means of the cluster centroids. Okay, and now the Dirichlet distribution allow you to basically draw the multinomial parameter, and here are examples of 3 draws like this. Okay, and if you combine these 2 stories together, you can basically now do the following. With a draw of 3 samples, then you again draw 3 points from this Gaussian distribution. And this actually makes a difference. When you actually take 3 points from a Gaussian distribution, what is the probability of each point? It is a continuous distribution. Therefore, any single draw has actually 0 mass, right? Therefore, you cannot say that that particular point, no matter how it be used, is having a probability associated with it. But now, if you associate with each draw from a Gaussian with a multinomial parameter, draw from the Dirichlet, then every point actually is associated with a mass. Okay, and all the mass add together actually equal to 1. Okay, that allows this Gaussian draw to be now taking a new function as a cluster centroid, because every cluster is going to happen with some probability, right? Because if you have 10 points, maybe 3 points is belonging to this cluster, then the probability is 1/3, or 0.3, right? And that's actually how we actually combine the Dirichlet prior and the Gaussian prior together to define a prior distribution of a mixture model. And if you have a different draw, then you can actually have a different set of Gaussian mixture, and likewise. Okay, so that's again what we began with by calling the Dirichlet distribution to be a vehicle to define distribution over distributions. Now let's study a few interesting properties of Dirichlet distribution. I want you to actually appreciate this kind of property. It's purely algebraic game, but I found them to be quite interesting in terms of how to manipulate Dirichlet. So I have a k-dimensional Dirichlet distribution. Okay, I state a rule first, but let me start from the. Actually, the rule is like this: if you originally have a k-dimensional distribution, you can coalesce any dimension in this k to make them one dimension less, or even more if you do it consecutively. And the rule is the following: you add two of the coefficients, two of the Dirichlet random variable together, and then you are going to have a k minus 1 dimensional multinomial vector, and they are going to follow a distribution which is defined by, again, the original set of Dirichlet parameters, but with the corresponding two Dirichlet parameters also summed together to become one parameter for that coalesced dimensions. Okay, so this is called the coalesce rule. I mean, I don't know actually the name of this rule. I kind of put the name here to make it implicit. And the way to prove is roughly, illustrated here, and you can see maybe a following rationale. So first of all, there is this relationship to a gamma distribution. If there is a random variable, following a gamma distribution. I mean, again, I'm not going to write down what is a gamma distribution. You can check the book. Then, if you have a k such gamma random variable, then their normalized form follow a Dirichlet distribution whose parameter is defined by the gamma parameter. Okay, so that's the first rule. Okay, k independent gamma distribution, a gamma random variable, follow a Dirichlet distribution if they are normalized. Okay, and now if I have two, a gamma random variable summed together, okay, then they are actually going to follow a gamma distribution with the parameter also changed accordingly. Okay, that's an interesting rule that you can easily prove by studying the form of gamma distribution. Okay, and then because of this and that, you can easily derive that you can collapse any pair of dimensions in the Dirichlet distribution with this same operation of collapsing the two corresponding Dirichlet parameters. Okay, that's one rule. How to basically shrink the dimension of a Dirichlet distribution. That's one thing. Then we can go opposite, how to expand the dimension of a Dirichlet distribution from smaller one to bigger one. And here I call them either an expansion rule or a combination rule. And it goes like follows. Suppose I have a k-dimensional Dirichlet, okay, with parameter alpha 1 to alpha k. Then I have one more parameter, theta. This is a random variable that follows a beta distribution. Beta is a two-parameter distribution, which is now parameterized in this way. I have a gamma 1, then I have a beta and 1 minus beta, assuming beta is between 0 and 1. So this is really a convex split. Okay, if my theta follows this particular gamma, this particular beta, then you can actually use this beta to now split, okay, one dimension in Dirichlet. You can basically split them according to theta and 1 minus theta to make the original pi 1 to be occupying now two spots, okay, in a new vector, new random vector. And then it also follows a Dirichlet distribution with a parameter, that is, also, distributing the original alpha 1 into two dimensions. And the way it's distributed is the same way that the beta parameter is set up. Okay. So it is very interesting. Because of this, you can now bring in, a fractional number to basically split a random variable in a distribution, in a k-dimensional distribution, to make them k plus 1 dimensional. Okay, and more generally, if the theta is not just a one-dimensional vector random variable, but it's by itself a n-dimensional variable, okay, therefore it is actually following a Dirichlet distribution itself, then you can use this theta vector, not a single theta, but a theta vector to split one dimension in another distribution, in another Dirichlet distribution in n ways. Okay, so this original pi 1 here now gets split into n pieces. Okay, and then plus the original k piece, k minus 1 pieces. And then this distribution gets further split. Okay, so that's actually the very interesting rule. One is about coalesce, one is about expansion of the Dirichlet distribution. Just remember that. And the interesting part is how the Dirichlet parameters are changing accordingly as a result of this split. And we're going to use this trick down the road to actually make our expansion. You probably can see where I'm driving toward already, right? So you do this once, you expand it by n, right? You do this twice, you expand it by 2n. You do it infinite times, you are going to now drive this all the way to an infinite dimensional space, right? And that infinite dimensional space is where we want to be defining a prior distribution on, because we are talking about now infinite dimensional models. Right. All right. And another thing, just for completeness of your knowledge, is about the renormalization rule in Dirichlet. If you actually have a k dimension node Dirichlet, and you just took away one dimension, and then they need to be the renormalized form of the k minus 1 dimension actually follows just this distribution with one of the parameters taken away. All right, with all that, let's, I think we have the device to move into a flexible open dimensional problem. Yeah.
Sorry, one slide back.
Mm-hmm.
That really is over 1 for capital K in the denominator?
Over 1 to, yes. Yes, it is not normalized. Okay, I'm just renormalized, but not meaning that this one is a normalized vector. Yeah. Or I could call it rescaling maybe. Right. All right. So, okay. So how many components do we want? And for this problem, so here is where we want to start. We want to now make sure that we always have more clusters than we needed. Okay, that's the first bit. And I want to be conservative in putting together a reservoir for cluster centroids. And then when data come, they will pick whenever it is needed. But otherwise, you can margin that one out by integration, right? And integration, of course, is an algebraic operation. In practice, we don't even need to do that. That's actually the beauty of this approach I'm going to show. And the other thing is that, you want to allow the setup to be random, okay, rather than a fixed setup chosen a priori. So it can be driven both by the data and also by the prior. So how to choose a prior? So here it means that you need to define an infinite prior for this pi. And we don't know how to do that, at least from our previous experience. And also we don't even know which way shall we actually, which particular property we want to make sure to enable a infinite dimensional prior over these weights or proportions. But we studied this Dirichlet quite a bit. We kind of like that property. It makes sense, right? It's a prior distribution over finite dimensional weights. And the infinite dimensional weights may follow something that is sharing a property as we see in the Dirichlet. So then let's see how can we actually now somehow engineer the Dirichlet distribution to make them suitable for our task. So let's start off from a two-dimensional Dirichlet. Let's suppose that in the simplest case, as we only consider a symmetric Dirichlet distribution. Okay, so alpha over 2. And we know the splitting law already, right? We're going to introduce the betas, okay, which follow, introduce some auxiliary or some pivot theta, which follows a beta distribution. And then we know that each of these beta can be used to split a dimension in the multinomial random variable into two multinomial random variable, and then accordingly split the Dirichlet distribution to be one more dimensional, right? So introducing these two beta, now we have the pi 1 split into two pi 1s each multiplied by theta and 1 minus theta 1. And the second pi 2 is going to be split by theta 2 into 2 pieces. And use the rule we learned from previous slides, we're going to now adjust the Dirichlet parameters accordingly. And you will find that at the end of the day, we have now a 4-dimensional Dirichlet distribution whose parameters are now alpha over 4. Okay, and you can repeat this, multiple times, and at the end of the day, you will find a k-dimensional multinomial whose prior can be defined by a Dirichlet defined by a single, parameter called scaling parameter alpha over k. Basically, every dimension in the Dirichlet is following the same Dirichlet parameter. Okay, this one is called scaling parameter. And you can imagine this k can go infinite. Then in principle, conceptually, we can imagine that this one is able to define a proper prior distribution over an infinite dimensional multinomial space. Right? So that's basically, again, here I'm hand-wavy because you don't actually write down that infinite form explicitly. You cannot, because it is infinite. You cannot really write it. But the truth is that you don't need to, because your data is finite. Therefore, you only need to keep those realizable things, okay, in your inference or in your database, which actually are used by the data. Say the centroid is actually having the data point associated with it. Right? For these other centroids which are still in the infinite space but never used by the data, you just don't need to store them. All right, so now we construct a proper prior, and this proper prior is no longer called a Dirichlet distribution. Okay, it is called a Dirichlet process. It has the following formal property. First of all, the pi is now, this is the whole thing about this process. It can actually contain 2 components. One component is this pi, which is the weight, okay, over components. And it is a multinomial, infinite dimensional multinomial vector, and following a Dirichlet distribution, but taking the limit to infinity. And then I also have something called a base measure h, because each of these dimension in the Dirichlet has to be associated with a real data point drawn out of it, such as a Gaussian Gaussianly distributed mixture centroid and stuff like that, right? So we let that particular component theta k to be drawn from the h, the base measure, which could be by itself a Gaussian distribution. Then a Dirichlet process is actually defined by this. It is called G. It is now the sum. It's an infinite mixture model you can see already, right? And sample, centered around the thing being just created from the base distribution, weighted by their weights. And here I'm talking about infinite dimensional. Okay, so this is an infinite distribution over the omega, which is the space of the original sample. Okay, so we write this as a Dirichlet process parameterized by a alpha, which is a scaling parameter, that is to use to define the Dirichlet parameters in here. And then the h, which is a place to draw your actual samples. Okay, so again, just to emphasize, Dirichlet distribution is a discrete distribution over a continuous space. Okay, it is different from Gaussian. Gaussian basically is a continuous distribution over a continuous space. Therefore, any point under a Gaussian has 0 mass. Okay, and the Dirichlet process is also a distribution over the continuous space, but it is a discrete one. It is basically like this and that and that. It is a point plus a mass on the point. The point comes from, or the position comes from a base measure, which could be a Gaussian, could be anything else, and then its weight is coming from a infinite dimensional Dirichlet distribution. Okay, so these 2 things together makes up the Dirichlet process. And now you can see why it can be used as a proper prior for mixture models, because now this point here has both a position and a weight. It is just perfectly suitable for being used as a cluster centroid. Right? This is the position of the centroid, and that's the prior probability of that cluster. Right? So that's the rationale. And again, this is just the illustration of what I just said. Under a Gaussian, under this continuous space, you have the base measure and also, the Dirichlet distribution for attributing weights on different draws from the base measure. And just for some high-level intuition, this beta, of course, will influence the spreadness of your draws. Okay, if alpha is a very, in fact, I think I meant to put different size of the alpha here. If alpha is a very small one, you don't get a lot of spread. They're likely to stick to just one of the Dirichlet. But if alpha is very big, then remember our earlier picture. When it's very big, you are going to spread the mass across to the corner, and you're going to get a lot of different draws. Okay. All right. So any questions so far? If not, let's just reinforce our understanding about the Dirichlet process in terms of their ability to partition a distribution space. So here I have a more kind of formal way of writing down the property of a Dirichlet process in a general sense. So let's suppose that I have omega, which is a space, okay, of anything, okay, it's a real space of anything that you want to model, and here we're not going to model any atom from that space, because the atom by definition has really very little, it has no mass, right? But we're going to talk about a partition over the omega space. So A to K is a partition. And then, under a Dirichlet process, the partition, of the space is distributed according to this distribution. Okay, if you have a K-partite, then it is going to be defined by a Dirichlet distribution whose parameters is a product of the alpha, which is the scaling parameter of that distribution, and also a unnormalized density, okay, of the A, the draw, under the base measure. Okay, so in a sense, it's like here, you are going to partition this space of real line, okay, and instead of just focusing on the points in here, you are going to now say, once I draw a point here and I have a mass here, I'm going to now occupy this entire space, okay, with a equal sized draw, and that occupies a weight. And then the second segment is another chunk in that space between 0 and 1, and it's taking the value of some number that I drew, but it is actually weighted by a value that I determined from this particular calculation. Okay. And let's see. Here, this actually property can be actually found from this very early paper for Gusen, who actually invented the Dirichlet process. And here I have another picture. Okay, it's really about making the event something that is shared by a volume in a distribution space. So here I have the whole space. It is now made two-dimensional rather than one-dimensional, so it's more easy to visualize. And I draw an event, and this one has a zero mass. But I'm going to now make this event a centroid, okay, of some grouping of many other possible draws. Therefore, I'm going to now associate that event with a mass. Okay, let's see. You don't have to worry about this. This is just a particular instantiation of what I meant. Just talk about this. Making this event, which is potentially a centroid of a cluster, and then we attribute that with a weight, it's a pi, and then this guy is basically telling you the area, okay, of of this whole chunk in the whole space. And what does it mean? It kind of means that down the road, if you actually draw data points in this space, this is a real space of real data. They're going to be all belonging to a cluster with here as the center, okay? And the whole probability mass of this cluster is going to be this big. Okay? So we are essentially partitioning a probability space. And this is a one way of partitioning, where when I mean one way, it means that the actual value or the position of each of the phi is drawn at random from Gaussian, and then the weights of each of the parts is also drawn at random from a Dirichlet distribution. I could have another partition which amounts to even different number of partites and also different areas for each parts. Right? I can have another partition. So a Dirichlet process is basically defining a distribution over all these different partitions, including the number of pieces, the weights of different pieces, and also the position of the centroid inside each of the pieces. Okay? So in AI, sometimes we call this a possible world. This is a possible world that the data can live in. And the Dirichlet process is essentially defining a distribution over all these possible worlds. Okay? And then we call a cumulative density function G to be a Dirichlet process if the possible world follows such a property in which the weight of each of the parts can form together a k-dimensional n-dimensional vector if I have n parts, and they are going to follow a Dirichlet distribution defined in this way. Okay, any questions so far with the Dirichlet process? Okay, if not, let's maybe study some interesting properties now. It is basically talking about a partitioning over a whole distribution space. Then how can we estimate a Dirichlet process? Have you ever seen, for example, real data that is telling you how a space is partitioned? Usually that problem itself is the question rather than the data, right? Therefore, Dirichlet distribution itself cannot be actually estimated, from real data, because the real data is not reflecting what is generated from a Dirichlet process. You need to have something else, okay? And also, usually, let's see, maintaining this G, okay, of Dirichlet process. G is what? G is, as we read before, is a process, right? We say basically the Dirichlet process is this is a G, which is based on a infinite dimensional summation, and it is talking about a distribution created from this process. You draw sample from a Dirichlet and then draw center from a base measure. Therefore, it is an implicit form. There isn't a very clean closed form expression of the G. So it makes it a little bit difficult to manipulate. So here I'm going to talk about another interesting property which makes the distribution more manipulatable, which is the following. Suppose I have already a partition, okay, generated up to now. And then I actually start to see actual observations, okay, resultant from this partition. Say, for example, I have this partition of the space, and suddenly I discovered an actual point in this space. Okay, and then what is the posterior distribution of the partition, given that you see a point in that space, in a particular part? Okay, so here we are going to make a connection from the prior to the real data, and it turns out that it is actually going to follow a Dirichlet distribution with the adjusted parameter. You just add this count into the corresponding dimension. Okay, so that's basically a posterior. And therefore we can now write a rule for the conjugacy of that reflects the conjugacy of a Dirichlet process. So a priori, we have this as a prior weight of the Dirichlet process, and here is the posterior weight of the Dirichlet process, right? Which actually is still a Dirichlet distribution, and then that allows us basically to now write down a posterior of the Dirichlet process after seeing one data point. It is actually a reparameterized Dirichlet process with the scaling parameter increased by 1, and with the base measure readjusted in this way. It is still a Dirichlet process. Let me just put it more specific. G actually follows a dp of alpha and h. Okay, then according to what we have here, the posterior of every partite is given one observation is going to be following this distribution. Then we can actually write down the posterior of the Dirichlet process with this using this reparameterized Dirichlet process. Okay, and you can see this and this take the same form. Therefore, it is a conjugate prior. Okay. Why this is interesting? Well, this is interesting because it gives you, something called a predictive distribution of data points based on existing data points and also the hyperparameters of the data. So what you have in the Dirichlet process is alpha, base measure, and maybe a few other data points that you already have sampled from the Dirichlet process. Then, now what you can do is to evaluate, a new data points, okay, under, a Dirichlet process that is learned both from the prior and the posterior. Okay, so here you can now write down P of n plus 1 given so this is what we call a predictive distribution. Okay, why this is interesting? Why we need a predictive distribution for that? So in here you can see something is gone already. This G is already gone. There is no place you can see the G explicitly, right? We don't have to actually define a marginal distribution of the sample given under the Dirichlet process. We're going to only worry about the predictive distribution of one new data point given the old data point and the prior. So first of all, we can find that this one can be written in a very compact closed form, as I'm showing in the next slides. And secondly, this is a very useful distribution field to perform inference, right? Remember, when we do GIP sampling or other MCMC-based inference, what distribution do we usually use, or what sampling procedure we actually use? We're trying to basically sample from one data point, one state, given the rest of the states, right? So this is actually such a distribution. It gives you the probability distribution of one state given the rest of the states and also the prior. Therefore, this distribution can be used for sampling from a Dirichlet process. All right, so maybe here I can make it more explicit. So I have now a priori, this is a Dirichlet distribution. and a posteriori if I have a web observation, then I change the Dirichlet process to be reparameterized. And under the so this is actually a 2-parameter Dirichlet distribution. And here, what you don't have is pi y. Pi 1 is a atom at, let's see. Okay, right. So suppose that we have, we begin with 1 point, okay, and this 1 point gets, a weight of pi 1 and a atom at theta 1. I just draw 1 point, okay, and then I'm going to now, look at the other atom, which is, 1 minus, pi 1. It's a 2-dimensional Dirichlet distribution, and pi star. And a priori, according to our Dirichlet process, it is following a prior distribution of this, okay, over the mass. Okay, this is parameterized by 0 and alpha. And now I'm going to see actually a example, which is actually this guy. Okay, and that basically means that pi 1 gets 1 more instances. Then you are going to add 1 count into that dimension. Remember our previous slides that the posterior is actually, trivially computed by, the prior parameter plus the pseudo count, the actual data counts from the data. Therefore, I have this increment. Okay, and now what you can do is to integrate out the pi 1, regardless of the value of that. It's only focus on the sample. Say you are going to draw a second sample, okay, from this same distribution. You draw 1 sample already, you are going to draw a second one. And what is the probability of seeing that second sample? Well, the second one, of course, depend on this guy. But this guy is also following a posterior distribution, which is determined by the data, right? And you can integrate this out and make the next one directly distributed dependent on data, like this. Let me draw a graphic model to explain this better. So we have a pi 1, okay, and pi 2, pi star, 1 minus pi 1. Let's sketch the 1-parameter Dirichlet distribution. I draw 1 sample, theta 1, okay, and this is observed. Then I'm going to, actually this follows a prior distribution, alpha. Clear about that? That's a graphic model. So now, after I draw this theta 1, I basically get a posterior of the P1 given theta 1 and also the prior alpha, right? And then I'm going to ask, what is the probability of drawing a theta 2? How should I do that? Well, I do that usually by saying what is the probability of theta 2 under pi 1, right? But we also know that pi 1 follows this posterior distribution. Therefore, we could bring in this pi 1 and also the alpha theta 1 and the alpha, and then integrate out the pi 1, right? And what does that mean? That means that this guy gets marginalized out. It's almost like the raw Black-Clarization step. And then this guy will be directly dependent on the first sample, right? So in this way, you have a predictive distribution of the next state, okay, conditioning only on the previous samples, but not the current posterior distribution of the distribution parameters, okay? And why this is interesting? Because it actually makes it is a collapse sampling step. You don't have to actually every time estimate the new parameter whenever you see a new sample. Okay. Remember our topic model procedure? We sample the z based on all the z's without revisiting the topic weights theta. This is the same idea here. And when you actually do the algebra and integrate out the pi y, you actually see a very interesting actually equation. The probability of sampling in the next sample, okay, is taking these two actually equations. With a probability 1 over alpha, it is going to take, atom 1 or class 1, k equal to 1, which is to repeat basically what the previous example was behaving. And then with alpha over 1 over 1, you're going to now get a new k, which wasn't implemented before. Okay, this is the so-called, the pi star dimension, which is not having any example yet, right? So the rationale now becomes the following. You basically, have some unknown dimensional distribution, and you don't actually have any sample. And then when you already see one sample, theta 1, you are going to assume that the distribution will be pi 1 plus a pi star, which I, do not have sample yet, but will be probably used. And then I'm going to ask, what is theta 2 coming from? What is the next theta belonging to? It's belong to this class or that cluster. Okay. Then this equation tells you that with probability 1 over alpha, it will actually go to this cluster. But with probability alpha over 1 over alpha, 1 plus alpha, it is going to use this previously unused cluster weights. Okay. And by that, you actually start a new cluster, okay, without even keeping that in mind. And this one can go further. If you draw the third example, you can see that now your denominator become 2 plus alpha because you have two samples in place already. And previously, you already, let's assume that the second sample come from, actually the second sample come from the second class. And then you are going to now have the third sample having some probability of belonging to the first class, some probability of belonging to the second class, and some probability of belonging to a third class, which is new one, which does not have any sample yet. Right. So what is the gist of that? The gist is that now if you keep, visiting the data points, okay, say I have n data points, and I want to give them cluster membership assignment, I don't need to know a priori how many clusters I need. I'm going to just use this predictive distribution to make them the assignment. This predictive distribution is a moving one, which is always built on the number of clusters I have implemented so far, plus one more that may be taking new samples. Okay, and then you are going to make the assignment to these two previously occupied cluster or a new one. And this iteration will go forever. Okay. So that's what we know as a predictive distribution. And this is the full general case. If you have n samples, then the predictive distribution of this n plus 1 sample will be following this distribution. It can go to any of the previous k cluster with a mass, with a probability proportional to the number of samples already in that cluster, normalized by n plus alpha, and with a residual probability of entering a new cluster with no sample yet, with probability alpha over n plus alpha. Okay, so that is a very, very detailed derivation on why a infinite extension of our Dirichlet distribution can allow you to keep growing cluster and producing a valid prior over infinite mixture models. Okay, and this is essentially this rich gets richer property. Bigger clusters are more likely to be occupied by later points once again. But again, the beauty about this procedure is that even an empty cluster to be occupied has a non-zero probability to be occupied. Okay, and now you can see the kind of behavior, the utility of this alpha. This alpha is sometimes called a scaling parameter. It tells you the tendency of initiating a new cluster when you see a new point. Okay. All right. So this is a pretty analytical derivation of the Dirichlet process, which is a little bit difficult to appreciate, to understand for initial users. But now I'm going to switch gear and tell you some more kind of a fun-driven story about how to use different metaphors to implement Dirichlet process or to understand that. But now with all this presentation earlier, you kind of know the mathematical root of these metaphors. Okay. So one of the metaphors is called the Poyer-Erm process. Okay, it is exactly about how to actually initiating new clusters without pre-specifying the number of clusters. So it is a process, that is telling you how to color a ball. Okay, suppose that you have a urn which has a lot of balls with unknown color, and you are going to draw it out and color it. Okay, and then the way you set color to different draws is exactly according to this equation. If you draw, you basically draw a color, draw a ball out, and because it is the first draw, you are going to assign a new color to it. And the next time you are going to draw it, you are going to actually see, whether it is how many colors already exist in the urn, and you are going to, basically color this new ball based on, your color breakdown already in the ball. Okay, so this is basically the way writing down the marginal distribution. That's the Poyer-Erm process. Here I have, a text script about how the procedure runs. The second story is a little bit more fun to appreciate, maybe easier to understand. It is called the Chinese restaurant process. It was invented by a Berkeley statistician who used to go to little Chinese restaurants in San Francisco very often, and he was impressed by maybe the way food was served in those restaurants. They seem to have an infinite number of dishes, infinite number of capacity of taking customers. Therefore, he was taking down this process. Suppose I have a first customer coming in. Okay, he would choose to sit on a random table, whatever, and then take a note on I sit on this table. Then the second guy comes in. Okay, he's going to choose. The second guy refused to come out. Okay, he's here. He's going to choose a table based on the following procedure. He's going to sit with the first guy with probability 1 over alpha, and sit with a new table with probability alpha over 1 alpha. Okay. And the third guy comes in. I don't know why he refused to come in. Okay, right, so he's going to follow this probability. Now there are 2 people in the restaurant, and he will be looking at the occupied table and sit there accordingly based on this probability. But he also has a small probability of choosing a new table. Then you can imagine at the end of the day, my I plus 1, my I's customer comes in. And so far, there are already I minus 1 people in the restaurant. Okay, and their breakdown is like M1 people in table 1, M2 people in table 2, and so forth. And they are going to now, choose a table based on the popularity of different table and sit there, and with a probability of sitting on a new table. And this is called the Chinese restaurant process. But what's more interesting on the Chinese restaurant process is that it is a clustering procedure which allow you to not only, sit tables, but also to define, some cluster-related quantity. For example, on the table, you are allowed to sample a dish. This dish is going to be shared by all the customers, sitting around a table. And you can imagine this dish being the cluster centroid of a group. Okay, and its value are randomly sampled from. Okay, and another interesting, insight from this Chinese restaurant metaphor is that it is actually defining a exchangeable distribution, okay, of the seating procedure. Suppose that the next time, all these customers come again, but they don't come at the same order. Maybe this guy comes first and that guy comes second. Once you run this process, you will find that they will be following the same partition. Okay, eventually they will actually fall into the same partition as you see in the previous day. Okay, and that means it is a exchangeable distribution which is not dependent on the ordering of the sample. And what does that mean? It means that now whenever you actually want to draw a predictive distribution for a new sample, you can always treat that as the last sample in this n customer, and assuming the other n-1 already there. Okay. And that's very important because when you do a Gibbs sampling procedure, right, you are going to now cyclically resample every random variable. Basically, you are going to resample every sitting position of this guy in different iterations, and in the second round, you don't have to now start again from empty table. You can just treat them as the end of the previous n customers and conditioning his choice based on the previous n examples. Okay, that's the second procedure. The third procedure is called a stick breaking process, and it is useful sometimes to motivate some approximations to this to the Dirichlet process. So here is what do we mean by stick breaking process? It says that a Dirichlet process here is actually coming from two independent processes. One is what is known as the stick breaking process. I have a unique stick to begin with. I'm going to break it into two. And the fraction of the breakage was actually drawn from defined by beta. Okay, and the beta actually is, in fact, a beta variable we can draw from a prior distribution. Okay, and so with this fraction, 0.4, I'm going to also draw a sample from a Gaussian distribution. Okay, and of course, the rest of that will be what's left for you to further break. So I'm going to now also draw a second one. Second sample, then I'm going to not breaking the whole stick again. I'm going to now take the remaining part, which is only 0.06. I'm going to draw a beta, which is the fraction to break. Okay, then I'm going to break this remaining piece and generate this 0.3, which is the weight for that pi. Okay, and then I'm going to draw a sample accordingly in here. Okay, so this is a process that you can break infinitely, and still, generating a non-zero weight, right? So with that, you actually now have a infinite dimensional, mixture model with their positions defined by random draws from a base measure G0, and with their weights generated by this so-called stick breaking process. Okay, and at the end of the day, the Dirichlet process is defined by a weighted sum of all these samples, and the weights are coming from this stick breaking procedure, and the positions are coming from random draws from the base sample. So why this is a useful metaphor, for some purposes? Well, one insight you can see is that when you are doing stick breaking process more and more and more, what condition you are running into? You're going to run into a smaller and a smaller mass remain for you to further break. And I'm almost telling you that if you break enough sticks, you can ignore the rest. And there isn't any point to generate new clusters. Therefore, it motivates the so-called truncation approximation to this process. You are back to finite dimensional distribution, but this finite dimensional is now motivated by this very special way of partitioning the weights across different clusters. Okay. All right, with all that, I think we are pretty much done with covering the Dirichlet process formalisms. And for completeness, I also provided the graphical models in here so that you can establish a operational correspondence, of what we said to, our previous, devices or tools which might be useful for inspiring inferences. For example, here I have a Poya-Ern or a CRG, Chinese restaurant process type of metaphor, where you have theta, which is the infinite-dimensional cluster centroids, and x being the data points coming out of the the centroids. And this theta is following the so-called G Dirichlet process in a very abstract way, which is defined by the base measure and the scaling parameter. So in here, how this and this cause that is a little bit mysterious. Here I have a stick breaking construction, which is a little more obvious. You have now a data, and which actually is having an indicator function of the cluster assignments. Okay, these cluster assignments are following a multinomial distribution, which is described by a stick breaking process as a prior. Okay, the pi is following a stick breaking process. And then the centroids of the cluster theta is following a base measure, which could be a Gaussian. Okay, and why this is interesting? Well, you can imagine that when you want to do inference and you want to do MCMC or other approximation, you become more explicit about which one to marginalize out. For example, if you want to marginalize out the pi without explicitly modeling the weights, you can now establish a predictive sampling of the next label based on all the previous labels, okay, using the kind of predictive distribution we just derived in previous slides. Okay, now let's talk about. I have 3 minutes left. The inference procedure. The inference procedure actually amounts to, figuring out, what are the hidden associations of all these points to the infinite number of parameters, right? So here we take the following generative model, which is called a Dirichlet process mixture model. It is one step beyond Dirichlet process. In Dirichlet process, we pretty much stop from here. We generate samples from the base measure and also their weights from the stick breaking process or the Chinese restaurant process. But in the Dirichlet process mixture, all these samples from the Dirichlet process distribution will be used as the centroids to generate actual samples, points in a mixture model, like these points. And this F could be a Gaussian distribution centered around the phi, which are the means. Okay. And now when we do inference, it is about figuring out the Zn associated with the X, meaning that to which particular cluster centroid they actually are associated with, and also how many Ks we are used. And then here I give you just one equation for you to sample this. So this is the predictive distribution of the label of a new point, okay, given all the previous data points, and also the cluster centroids. And you can see actually a pretty intuitive predictive distribution. It is now made into 2 pieces. If this K equals to one of the Ks that is already present in previous samples, then it is going to take a weight. In fact, I haven't written here. It should be more explicitly this plus alpha. Okay, this is the the predictive weights we actually had for the previous Dirichlet process predictive distribution. And then I have one more piece, which is this part. This is the likelihood of this new data point under the chosen centroids. So at the end of the day, it really means the following. If I'm going to group a new point x star into any of the possible Chinese restaurant tables, I'm going to follow 2 laws. One is the so-called rich gets richer property, which is just a priori. A priori, before I see actually the position of these points, I'm going to group it based on rich gets richer. It gets to the most popular table without looking for anything else. But if I actually know the coordinate of the x, I'm going to also see whether this particular point is compatible with the center in each of the table. And it is the product of these two contributors that determines whether this point should be assigned to one of the tables. Okay. So a likelihood function plus a prior distribution of their property. And if I want to also compute the probability of assigning to a new table that is not associated with any point before, then I have this alpha residual over n plus alpha. And what is this? Well, this is basically the collapsed probability of the new point under the base measure. Because this cluster hasn't been occupied yet, therefore its center is non-existent. Right? It should be drawn from a prior distribution. It can be taken any value. Therefore, I can basically integrate it out under the prior base measure. Okay? So that defines the marginal probability of the points, only given the prior weights. And then you do the sampling on and on for every data points cyclically, and you are going to converge to a particular point. Okay. All right. I have a few other ideas about how to do sampling, but this is not beyond the scope of today's lecture. We can say a few words next time. In fact, in next lecture, I'm going to bring you a real example that we used. We actually tried to solve before using this technique, which can show you the advantage of this process over a number of competing methods. Okay. All right. See you on next week.